So the next part is about tectonic plates. So the Earth's rigid lithosphere is broken up into pieces called tectonic plates. And these plates float on top of the plastic asthenosphere. So remember, the asthenosphere is a ductile solid layer. So these rigid tectonic plates float on top of that. And this map shows you the major plates. You have the Eurasian plate, the Pacific plate, the North American plate, South American plate, Antarctic plate.
Professor, I'm sorry, you said the what solid layer?
Ductile. Here. Ductile solid. So ductile means it's like movable, like pliable, kind of like taffy, like really hard caramel or taffy, but it's still a solid. So it's considered kind of like a plastic material in a different way than what we actually call like pieces of plastic that we see in everyday life. Plastic means more like a ductile solid. That's what plastic actually means. Okay, so again, these are hard, rigid pieces of land, of lithosphere, and they're floating on top of this ductile solid that we call the asthenosphere. So they're able to actually move around the Earth. And this is another map of the tectonic plates, and the boundaries are shown by these lines here. And there are arrows that show the direction of if the plates are separating from other plates that they're next to, or if the plates are moving next to each other, but in opposite directions, or if the plates are coming together towards each other. So in different spots, like in the North American plate is moving away from the Eurasian plate and away from the African plate, for example. Those are moving away from each other. But then like the Eurasian plate and the Pacific plate are moving towards each other.
What is causing them to move?
That is something we're going to go into a lot more detail in a later chapter. But you have the driving force is, you have something called ridge push, and you have a slab pull, and also it's driven by convection. But those are terms that we're going to go into more detail later on, because there's like a whole long story behind what those mean and how they work. But that's a really good question. So this just goes into a little bit more about the plate boundaries. Again, the boundaries are where tectonic plates meet other tectonic plates. So a convergent boundary is when plates are colliding with each other. Divergent boundaries are when the plates are moving away from each other, and actually new crust forms at that center where the plates move away from each other. There's volcanic eruptions there. And then you have transform boundaries, which is when plates move next to each other, but in opposite directions. And then this just shows you another diagram of the various plate boundaries and a little bit more detail. And then in another chapter, we're going to go into this in a lot more detail. So again, here is a convergent boundary where plates are moving towards each other, and one of the plates is actually going to sink down into the mantle. And then that rock that goes into the mantle is going to start to melt and get recycled back into the mantle. And then the divergent boundary is where the plates are moving away from each other, and you have new rock forming at that spot. That's called a mid-ocean ridge. And by the way, where this plate is moving underneath the other one, it's called a subduction zone. Okay, but this is just the basics, just an introduction. We'll go into this in a lot more detail later on in another chapter. So now we have minerals. So minerals are the building blocks of rocks. What is a mineral? There are 5 criteria for a substance to meet in order to be considered a mineral. Minerals have to be naturally occurring, inorganic, solid, have a crystal structure, and have a specific chemical composition throughout, or uniform or homogeneous, meaning it's the same thing throughout the whole piece. So this is the main outline of the 5 criteria, and then I'm going to go over each of these in a little bit more detail. So naturally occurring is not something that's made in a lab. It has to be formed in nature. You do have synthetic minerals, but we call them synthetic minerals because they're made in a lab. They're not found in nature. So those are a little bit different because they're not technically naturally forming minerals. Inorganic means non-biologic origin. Minerals do not include materials related to anything that is or used to be alive. So for example, seashells, coal, pearls, amber, those are not minerals because they are biologic in origin. Now, sometimes seashells is considered to be a biogenic mineral because it's made of something called calcium carbonate, but it forms as an excretion by mollusks, for example. Mollusks include things like clams and oysters. So seashells is a little bit of a different category, but we're still, for the mineral chapter, going to consider seashells to be not really a mineral. Then solid means it's not a liquid, it's not a gas, it's something that's firm and stable in its shape. Then crystal structure, which is also called atomic arrangement. That's when atoms in a solid material are arranged in a repeated pattern. We could also call that a crystal lattice. For example, salt. Salt is a mineral, actually. So here's salt. Is composed of sodium and chlorine atoms that bond together in a cubic shape. So no matter how large a salt crystal is, it's just cubic shapes repeated over and over and over. So that's the crystal pattern, or the crystal structure of salt is a cube. So the jungle gym on the bottom left is kind of like salt crystals, where it's just cubes repeated over and over and over and over. And then the jungle gym on the right is triangles. So I use these as an example for crystal structure. The one on the right is not necessarily a representative of a real mineral, but it does show you a repeated pattern of these triangles that's repeated over and over and over, etc. So here you have sodium and chlorine atoms, and they combine to form salt, and they form in a cubic shape, and it repeats over and over and over. So that's what it means with in terms of the crystal structure or the atomic arrangement. So not all solid materials contain atoms arranged in repeated patterns. Solids like that are called amorphous. Amorphous would look like on the bottom where it says non-crystalline or non-crystalline, where the atoms are kind of just more randomly oriented. And then crystalline, it's more of a structured, repeated pattern. And then on the right, you have a similar example. So you have a crystalline repeated pattern, and then you have an amorphous solid where it's kind of more randomly oriented. An amorphous solid, an example would be glass, because atoms are not arranged in a repeated crystal structure in glass. Natural glass is actually a rock called obsidian, and we'll talk about that in the igneous chapter. And the fifth criteria for something to be considered a mineral was chemical composition. A specific mineral will always be made of the same basic composition throughout, and we call that homogeneous. Examples: quartz always has the composition of SiO2, which means 1 silicon atom and 2 oxygen atoms. Salt always has the composition of NaCl, which is sodium and chlorine atoms. So there's a specific composition that is going to be related to a particular mineral. And mineral composition is shown using a chemical formula, which is just shorthand of showing the numbers of the different elements that are in the mineral. So in this photo here, this is a mineral called orthoclase, which is a type of feldspar mineral. It's also called potassium feldspar. And this is the formula for that mineral. So it has KAlSi3O8, which means it has 1 potassium atom, 1 aluminum atom, 3 silicon atoms, and 8 oxygen atoms. So all samples of orthoclase feldspar have this composition, this chemical formula. There may be minor impurities in a mineral's composition though, and this leads, for example, it leads to differences in color, but the main composition will remain the same. So for example, you have the mineral called corundum, which is Al2O3. Corundum is a colorless mineral. So in its pure form, it does not have a color, it's see-through. When corundum contains a slight impurity of chromium, then it actually turns into a red mineral, and that's called ruby. So ruby is a red variety of this corundum, which is normally colorless in the pure form. But there's not enough chromium in the chemical composition for it to change like the way the formula is written. It's still Al2O3. There's just a little tiny bit of chromium here and there throughout the mineral, but it's such a tiny impurity, it's not, you don't like add chromium to the chemical formula because it's not really enough. It's just a tiny impurity. When corundum has titanium and iron in it, it turns blue, and that's what sapphire is. Now, by the way, any corundum that's not red is called sapphire when you're talking about the gemstone industry. So like blue is sapphire, but then you have like yellow sapphires, pink sapphires, right? I've even heard of white sapphire. Okay, so basically in like the jewelry or the gemstone trade, they call it all sapphire unless it's red, and then it's ruby. Now, quartz is another mineral that can vary in color. So amethyst is a variety of quartz that's purple because of iron impurities. So that's purple amethyst. And then you have rose quartz, which is pink, which has iron and titanium impurities. Now, quartz can also come in like a yellowish amber color. It can come in brown and be called smoky quartz. It can come in green. There's different colors of quartz. So here we're just going to do a brief chemistry lesson before we move on to discussing bonding of atoms and discuss how minerals actually form. So why do atoms bond together to form compounds, including minerals? That's what we're going to answer. So atoms contain a nucleus, which is made up of neutrons, which have a neutral charge. So here's an example of a carbon atom, and the nucleus is the center here. So the little red circles with no charge are neutrons. And then the protons are the little blue circles with the plus signs. And then you have surrounding the nucleus and kind of spinning around the nucleus, you have electrons, and those have a negative charge. And the protons equals the number of electrons. Now take note that the carbon atom has this inside circle and then an outside circle, and we call those shells. So the outer shell of the carbon atom has 4 electrons. So keep that in mind. So now we're going to talk about bonding of minerals and how minerals actually form from atoms bonding together. So you have ionic bonds, covalent bonds, and van der Waals bonds. Ionic bonds are bonds that involve the attraction between ions with opposite charges. So ions are atoms that have a charge. Okay, so this atom here is neutral, but some atoms can either gain an electron or lose an electron, and then they would, or multiple electrons, and then they actually gain a charge. So in this case, the sodium atom loses an electron, the chlorine atom gains that electron. And what that does is it turns the sodium atom into a positive ion because it loses one of its negative charges. So then it becomes positive. The chlorine atom gains that negative electron charge, and then it becomes a negative charged atom, which we call an ion. Then what happens is the sodium atom is positive, the chlorine atom is negative, so then they're going to want to bond together. They get attracted to each other because opposites attract.
So it's always going to be one positive and one negative, correct?
Yes, it's always going to be opposite charges that are attracted to each other. So in this case, the sodium and the chlorine will bond together and form salt. This is the same type of salt that you like cook with. You know, you put salt on French fries or whatever. This is salt. It's sodium and chlorine. Now, actually, when you eat salt, you're dissolving this bond. You're actually breaking this ionic bond, and you're tasting the chlorine atom on your tongue. and that is what you taste as being salty. So you're able to break this bond. Ionic bonds can also break if you put salt in water. The water is able to break up the ionic bond of salt. Okay, so to continue the ionic bonds, an atom with a charge is called an ion, right? And the charge comes from either losing or gaining electrons. So this is what I was just talking about. If a sodium atom loses an electron, it becomes positively charged. Here I wrote Na+1. A nearby chlorine atom can gain the electron and become negatively charged, Cl1-. Usually, if the number is 1, you don't write the 1, you just write the plus or the minus. If the charge is greater than 1, then you write the number. And then the Na and the Cl are attracted together because of their opposite charges.
So what mineral would be associated with an ionic bond?
Salt. And the mineral name for salt is halite. Oops. So like the salt that you use in your kitchen is called, it's the mineral name for salt when you're talking about it as a mineral, it's called halite. Okay, so this attraction between the positive and the negative charges bonds the two ions together, forming the compound salt, NaCl, which is neutral. It does not have a charge. And again, that's salt, and it's called halite when you're referring to it as a mineral sample. And then this is, I showed you this diagram earlier, but it's labeled, the chlorine is the larger circle and the sodium is a smaller circle. Now, by the way, when you're talking about the chlorine, when the chlorine has a charge to it, you call it chloride. So it's, where it says chlorine, you may also hear the term chloride. So it's also known as chloride. Then you have covalent bonds. That's when atoms share electrons with other neighboring atoms in order to fill their outer shells. So in this case, again, this was the carbon atoms. This is the same carbon atom that I showed you here. The outer shell of the carbon atom has 4 electrons. See, 4 electrons. So a complete outer shell of any atom has 8 electrons, or most atoms actually. Noble gases have this, such as neon or argon. They have 8 electrons in their outer shell. Most atoms do not have complete outer shells. So a major goal of many atoms is to bond with other atoms in order to share electrons so that they can get completed outer shells. So again, we're looking at the same diagram of the carbon atoms. Now, when you count the outer shell electrons of the carbon atom, we got 1, 2, 3, 4, 5, 6, 7, 8. Carbon has 4 electrons in the outer shell, but when it shares electrons with neighboring carbon atoms, it's able to fill its outer shell and be complete with 8 electrons. So in this case, the carbon atoms are sharing electrons with each other, and the shared electrons are circled with this red circle here. And this is called covalent bonding. Covalent bonding is when atoms share electrons. Ionic bonding, we talked about with the salt, is when atoms of opposite charges are attracted to each other. So covalent bonding is a stronger bond because they're sharing electrons. It's harder to break a covalent bond than it is to break an ionic bond. Again, ionic bonds, for salt, as the example, you put it on your tongue and it dissolves the bond. You put salt in water, it dissolves the bond. Covalent bonds don't necessarily just dissolve because you put the material in water. It's a stronger bond. Then we have something called van der Waals bonds. This is a weak type of bonding between regions of molecules where there are opposite charges. So in this case, you have a water molecule on the left and a water molecule on the right. So water molecules have charges on opposite sides of the molecule. So on one side of a water molecule, it has a negative charge. On the other side of the same molecule, it's more positive. So that causes water molecules to be attracted to each other and kind of stick to each other. Because like the positive end or the positive side of a water molecule is attracted to the negative side of another water molecule. So that attraction is van der Waals bonding.
So it has 3 molecules?
In this case, on the left, that's one water molecule. It has 3 atoms. So H2O is 2 hydrogen and 1 oxygen.
Does it always have 3 atoms or no?
Water? Water is always H2O, which has 3 atoms. But the van der Waals is not only for water molecules, it does go for, there are other materials that have van der Waals bonds. This is just an example of how a van der Waal bond works.
Isn't this also called just a hydrogen bond? Or is that something completely different?
Well, in this case, I want to move on and show how this relates to minerals. So I'm going to call it van der Waals bonds.
Okay.
But in the case, when you're just discussing like water molecules, it's a little bit of a different way of describing it. But I'm going to go ahead and show you with other minerals how this is. So we're going to use van der Waals. So when you're talking about soft minerals like graphite, mica, or talc, the van der Waals bonds hold mineral sheets together. And I'll show you. So the sheets, in this case, these are carbon atoms, and they are sharing carbon atoms with each other, and they are covalent bonds within this one layer of this mineral here. This is a layer of mineral. Okay, those are covalent bonds. Those are strong. But this layer of the mineral is bonded with this layer of the mineral, and then these 2 layers are bonded together. And then you just have layers and layers and layers bonded with each other with van der Waals bonds. And those are weak bonds, and the mineral could actually break very easily along these weak van der Waals bonds. So what you can do is actually peel some minerals apart you peel the layers apart. Or in this case, this is graphite. So when you take a piece of graphite and you rub it on a piece of paper, you're breaking the van der Waals bonds and leaving little pieces of the graphite behind on the paper. But you basically just broke a bunch of bonds. And then there's another mineral called mica in this picture on the left, which peels into sheets. And that's also related to what I was just saying with the sheets and the van der Waals bonds. So now we're going to talk about physical properties of minerals. Physical properties of minerals are mainly determined by the crystal structure or the atomic arrangement or how the atoms are bonded. That is going to give us most of the physical properties of a mineral. And we'll go over some examples and how this works. So physical properties, by the way, some examples include how hard the mineral is or the ways that the mineral breaks. So here you have halite or salt. It breaks into cubes, and that's related to the crystal structure that I showed you with that jungle gym picture. The crystal structure of salt is cubes. It's cubic. So when you're talking about salt crystals, it breaks into cubic shapes, little tiny cubes. Okay, so the physical property of halite breaking into cubes is related to the arrangement of the atoms. Mica peeling into sheets is related to the bonding where it's similar to this, where you have like a sheet that's covalent bonds, but then in between the sheets, you have the weaker bonds that you're able to like peel the mineral. Okay, so this physical property of having thin, flexible sheets is related to the atomic arrangement of the mica. So while we're talking about physical properties, I want to go into the concept of polymorphs. Polymorphs are minerals that have the same chemical composition, but the atoms are arranged in a different crystal structure. And because physical properties of minerals are mainly determined by the crystal structure, polymorphs have different physical properties, even though they have the same composition. Now, what does all this mean? I will show you with examples. So, for example, graphite. If you ever took an art class, you may have used a graphite pencil, like a stick, a graphite stick that's made of graphite. Graphite is one of the softest minerals on Earth. It's dark gray, it's greasy, and it has a metallic luster. So here's a picture of graphite on the bottom. Just make it bigger. Okay, so that's graphite. Graphite is made of carbon atoms. Like that's the composition of graphite. It's just carbon atoms. And this is how the atoms are arranged. Okay, you have strong bonds making these sheets of graphite and then weak bonds holding the sheets together. So that's graphite. And again, keep in mind, it's only made of carbon. Does anybody know of another mineral that's only made of carbon atoms? Does anybody know another mineral made of carbon atoms?
I'm gonna. Oh no, mineral. Never mind. Sorry, I was gonna say carbon dioxide.
Okay. Um,
Diamond.
yes. Yeah, a hint is that it's on the next slide, actually. But yes. Yes, thank you. Diamond. Thank you. Yeah, diamond is the hardest mineral on Earth. It's colorless, but it's also only made of carbon atoms. Okay, so this picture of a diamond and this picture of graphite, they look extremely different. They almost look like opposite types of minerals. This is one of the softest minerals. It's dark gray, it's metallic. This is the hardest mineral. It's colorless, it's sparkly. They are both made of exactly the same thing. They are both made only of carbon atoms. So this shows you that composition is not really what is determining the physical properties. It's the way the atoms are arranged. So in the diamond, the atoms are all arranged in a really strong, tight-knit structure, really strong covalent bonds throughout. So there's no layers involved here. There's no ionic bonds or van der Waals bonds. It's all just strong covalent bonding. And it has to do with how the mineral forms in the first place, which we could talk about another time. But diamond involves a lot of pressure. Well, we could just mention it now, but diamond involves a lot of pressure. So in this case, the carbon atoms are able to be bonded more like tightly compact. So it gives you a stronger bonding, and that's going to cause it to be a harder mineral. But graphite does not form under as much pressure, so the bonds are not as like tightly compact, tightly knit. Okay, so they're both made of only carbon atoms, but they are very different minerals, very different mineral properties. So I thought that was pretty interesting. And we will discuss polymorphs at another time, other polymorph examples. For now, I want to just get into different types of minerals. And then when we do the mineral lab, we're going to get into this further when we do the mineral lab next week.
Professor, before you continue, can you repeat what the mineral was for covalent bonds?
This one was diamond. Is that what you're
No, for covalent bonds. I know you said that the halite was which is salt, was the mineral for ionic bonds. I didn't hear what you said was the mineral for covalent.
Oh, I see what you want. Okay, so one of the examples of an ionic bond mineral is salt. And
No, yeah, I got that.
right.
I'm looking for covalent.
Right. So then an example of a mineral that has covalent bonds could be diamond. So these here are covalent bonds.
Okay, got it. Thank you.
Long covalent bonds. Okay, so yeah, these are just examples. But then also when you go back to the graphite, these are actually also covalent bonds within the sheets though. But then it's the weaker bonds holding the sheets together. So there are a lot of mineral examples for covalent bonds. But yeah, we'll add that there. Okay, so types of minerals. There are common mineral groups. The most common mineral groups that we're going to discuss in this class are the silicate minerals and carbonate minerals. Silicate minerals include silicon and oxygen. Silicon and oxygen are the most abundant elements in the Earth's crust, as we discussed earlier in this lecture. A combination of oxygen and silicon is called silica. Minerals containing silica are called silicates. Pure silica is quartz, or SiO2. Silicates are the most abundant mineral group at the Earth's surface. So 95% of the Earth's crust is made of silicate minerals. So the atomic arrangement of silicates is the silica tetrahedral. It's also called a tetrahedron. And it looks like a pyramid. So the top picture is just showing you the ball model of a tetrahedral, where it shows you the atoms in the shape of balls. Then you have the ball and stick model, which shows you a little bit more, it's easier to see what's going on in the ball and stick model. But a silica tetrahedral has SiO4 as the chemical formula. So it's one silicon atom and 4 oxygen atoms. So here are the 4 oxygens are in the red, and then the silicon is in the middle. So when you, the ball model, you can't see the silicon. It's like stuck in the middle there. You can't see it. So this is the basic building block of all silicate minerals. Now, when it's plural, we call it a tetrahedra. So there's like all these different words involved: tetrahedral, tetrahedron, and tetrahedra. Now, the -4 here means that the SiO4 has a -4 charge, actually. So the silica tetrahedral has a -4 charge, which means it's going to be able to bond with other stuff, either molecules or atoms. By the way, the tetrahedral can also be drawn like this. So if you're going to draw it by hand, this is how you could draw it, where you have the 4 circles are the oxygens, and then the 1 circle in the middle, the smaller circle, is a silicon atom. Now, I just want to quickly point out, there were different times in the review sheets where I ask you to sketch things. The reason for that is it helps you remember things better when you sketch diagrams. Also, I sometimes have you put things in a chart, like I have an empty chart and you'll fill in answers. When you answer in a chart format, it helps you remember things better as well, especially if you're a visual learner. Those things will help. Okay, so the silica tetrahedron has a -4 charge, so that allows it to combine with positively charged ions or other silica tetrahedra. In that case, they share oxygen atoms. So what happens is you get these chains of silica tetrahedrons, tetrahedra, which was the plural. So sometimes you have a single chain where each of these triangles represents another one of these silica tetrahedra. And when they share the oxygens, in this case, they're sharing 1 oxygen with another tetrahedra. So it forms what's called a single chain. And that gives us minerals such as a mineral called pyroxene. And then sometimes you have a double chain in some minerals, a mineral, for example, called amphibole. That's a double chain. And then sometimes you get a 2-dimensional sheet which would be mica, for example. So that's mica. And then this would then, let me show you going back a bunch. We'll keep going back. When you look at a structure like this, you would have a sheet. This is not mica, but you would have a sheet on top, like that sheet I just showed you, and then you would have a sheet underneath, and those sheets would be held together by weak bonds. And then that is how you get mica that peels into sheets. Mica would be on the left here. Okay, so that's your sheet. And again, this sheet would then be like layered on top of other sheets, all bonded weakly together. Then you have a three-dimensional framework for minerals such as quartz and feldspar, which are like strong, hard minerals. These are some common silicate minerals: quartz, feldspar, and muscovite mica. So this picture up here shows you some quartz, different colors. You have milky quartz, clear quartz, and rose quartz. Then you have plagioclase feldspar, potassium feldspar, and here's some muscovite mica. So these are common silicate minerals. Then we have carbonate minerals. Again, going back to that first slide about the common mineral groups, silicates and carbonates, right? So now we're gonna go over carbonate. Carbonates are minerals that contain the negatively charged carbonate radical, which is just CO3 with a -2 charge. So this is what we call carbonate, CO3 with a -2 charge. A common carbonate mineral is called calcium carbonate, which has the CO3, which was a -2 charge. It combines with calcium, which has a +2 charge. So those two combine, and then you get CaCO3. So calcium carbonate is a common carbonate mineral. Common carbonate rocks include things like limestone and marble. And then mollusks, such as clams and oysters, make their shells from calcium carbonate. The common mineral name of calcium carbonate is calcite. And this is an example of what calcite looks like. It typically is colorless, and it's a rhombic shape. It looks like a little parallelogram or a rhombus. So that's the mineral called calcite. An easy way to determine if a mineral is calcite is to apply a drop of hydrochloric acid on it, and then you see if it forms air bubbles. That's from carbon dioxide. So in this picture, someone dropped a little bit of hydrochloric acid on a calcite sample, and you see gas bubbles fizzing. That's a chemical reaction that happens, that you're dissolving the calcite a little bit, and it releases carbon dioxide. So if you go back to the carbonate, CO3 is similar to CO2, which is carbon dioxide. So that's where the carbon dioxide is coming from. It's coming from that CO3. So here are some other minerals. We have malachite. This is what malachite looks like. It's a nice, pretty greenish color. And it contains copper. So it's actually a copper ore, O-R-E. Ores are rocks that you get metals from. So here's a picture of copper, just to show you copper, right? Okay, so that's malachite. Asbestos is actually really useful due to its insulating properties, but it could also be harmful because of the sharp fibers. So if someone were to breathe in the sharp fibers, it could be dangerous. Beryl is emerald if it's green, and aquamarine if it's blue. So those are common gemstones. It's a precious gemstones. Sulfur is a mineral that smells like rotten eggs. Okay, so then the rest of this is all about how to identify minerals. So we can examine physical and chemical properties of minerals in order to identify them. And this section of the lecture is going to be helpful when we do the mineral lab. So here's a list of some physical properties of minerals like luster, hardness, streak, magnetism, color, and feel. How does the mineral break? What's the density? And what's the crystal form? So luster is how light is reflected off of a mineral surface. So you either have metallic or earthy and dull, or you might have non-metallic examples like greasy, waxy, glassy. So here is a mineral, it looks like metal, so that's metallic. This is earthy and dull looking. It doesn't reflect any light. This is glassy looking. Okay, so this is luster, just how light is reflecting. Streak is the color of a mineral when in powdered form. So when you scratch a mineral against a ceramic plate, it leaves a powder behind. If the mineral is softer than the ceramic, then it can leave a powder. The color of the powder is what we call streak. In this case, this mineral on the left is leaving behind a reddish brown streak. On the right, this is like a dark charcoal gray or a black streak. If a mineral is harder than the streak plate, it's not going to leave a powder behind. In that case, you would have to grind up part of the mineral to see what the powder color is. Then these are just examples of crystal shapes or crystal form. As crystals grow, they develop into their crystal shape that's based on their atomic arrangement. Minerals will form in their true crystal shape if they do not have anything impeding their growth. For example, within a rock, little mineral crystals are going to bump into their neighboring crystals as they all grow together. So within a rock, many times you don't see the full true crystal shape. But in this case, these are quartz crystals. These were able to grow without anything impeding their growth, so they were able to grow with their crystal face. That is what we call euhedral. That's when crystals grow with their well-developed crystal faces. That's, again, when there's nothing preventing the mineral from growing into its crystal shape. So inside a geode, which is a rock that's like hollow inside, or in a cave, you're able to get crystals that form into their true shape. So that's euhedral crystals. Anhedral crystals are crystals that were restricted when they grew, so they don't develop their crystal shape. That's going to be what you commonly see when you look at rocks. You're going to see like little tiny pieces of crystals that don't really show the crystal shape. Now you can look at the crystal faces and that actually helps you identify crystals. So for example, quartz crystals have this like pyramid, not really pyramid, kind of looks like a pyramid. Here, I'll go back, right? It kind of looks like this. That's typical of a crystal of quartz. And then you can actually look at the angle between the crystal faces and it's going to be the same angle all around, for example. Then we have breakage. Cleavage is when a mineral breaks along planes of weakness within the crystal structure. For example, mica breaks along smooth planes of weakness between mineral sheets. Or salt breaks along cubic or 90-degree cleavage. Then we have fracture. Irregular fracture is when a mineral breaks randomly. Conchoidal fracture is when a mineral breaks along smooth curved surfaces. So here's a smooth curved surface. And here's mica being peeled into sheets. Here is a mineral that breaks into 90-degree angles of cleavage. Here's more 90-degree angles. This is salt or halite. Calcite breaks into rhombic shape, or this we call not 90 degrees or rhombuses. Okay, so it actually, if you break this piece, it'll break into smaller pieces the exact same shape. And if you look more closely, you can kind of see fractures within the crystal. So that it kind of already got a little bit fractured. So like if you were to just touch this crystal, it might actually just crack along that fracture. So minerals could have perfect cleavage, where it's like a perfectly flat side like this that it broke on, or you might have not as perfect, where you might see like little staircases on the surface of the mineral, but it may not be like perfect flat sides. Then we have hardness. Hardness is a mineral's resistance to being scratched, and we use Mohs hardness scale, where we compare materials that we know the hardness, like a piece of glass or your fingernail or an iron nail, and we compare it to minerals that we have in front of us. And again, we'll go over this again in lab as well. But this is the table of Mohs hardness scale. So talc is a 1, diamond is a 10. And then here are different tools that you could use in the lab room to help you determine the hardnesses of minerals. Oops. Okay, and then here's just some diagrams using different tools like your fingernail or a little knife blade. And so you basically see if the tool scratches the mineral or not. Then some minerals are magnetic. So this is a mineral called magnetite. So that's magnetic. Specific gravity is referring to the density of mineral compared to the density of water. When we look at minerals, we basically could use what's called the heft method, where you hold a mineral sample in your hand and you basically see if it feels heavier or lighter than others. Some minerals have a specific feel. So like graphite and talc have a greasy, oily feel to them. Kaolinite will feel powdery. And then we could talk about color. Color is only helpful for identification of minerals that are only found in 1 or 2 colors. For example, sulfur is always yellow. So a mineral that is yellow is easier to identify, mainly using its color. Also because most minerals are not yellow. In contrast, quartz and fluorite can be found in several colors, making it more difficult to identify based on color alone. That's actually spelled incorrectly. That's how you spell fluorite. Okay, so here's what I'm talking about with fluorite. Fluorite can come in yellow, purple, blue, green, clear. So you're not going to use color as a way of identifying fluorite as easily as you use color to identify sulfur. Okay, and then chemical properties of minerals, which are based on the chemical composition, we could talk about the odor of anything that has sulfur in it. So the mineral sulfur smells like rotten eggs, but then there's another mineral called sphalerite, which contains sulfur in it, which also smells like rotten eggs. Reaction to acid, which is relevant to carbonate minerals, which I showed you a few minutes ago. And taste. So if you have halite or salt, it's going to taste salty. That is a chemical property. And that brings us to the end of the lecture. So what you're going to do between now and next time we meet, you could read through the review sheet that corresponds with the lecture notes. The review sheet is on Blackboard. Answer the questions. Keep in mind it's not homework and I will not be collecting it. But if you want to, you can come to the Science Enrichment Center for tutoring if you're available and go over the answers. But if you do that, I would like you to have most of it finished or that you finish it on your own during the Science Enrichment Center tutoring. And then I could answer any questions you have about it. And then you're also going to follow the syllabus to see what to read in the textbook. And you're going to do that throughout the semester.